Welcome back, everybody. We are going to look at a regioselective Markovnikov reaction that is non-stereospecific. This is going to be addition of hydrohalogens of alkenes. We would do hydrohalogenation and then we will do the hydration. For the hydrohalogenation, it's typically HCl, HBr, and HI. We don't typically do HF. So let's go. Let's talk about HX additions to alkenes. Here's an example. Now, we are also going to do a bit of naming as part of naming, I would say, not a whole lot. And, go along with the naming as it progresses, it gets more complicated. So 1, 2, 3, 4, 5, 6, 7, 8. Should we number it this way or this way? In this case, there's absolutely no doubt. Alkenes get higher priority, which means they get lower numbers. Alkenes get higher priority over alkanes any day. So over here, we are going to name this then 1-octene or oct-1-ene. So here are 8 carbons strung up like this in a long chain. And at the very end, there's a terminal alkene, right? This terminal alkene, if you look at it, has got a carbon that has 2 hydrogens and a carbon that has a hydrogen and a alkyl, long chain alkyl group. It just matters that there is an alkyl group here. It doesn't really matter how long the chain is, whether it's 3 carbons or 25 carbons, the reaction is going to be the same because the reaction is going to be just centered around this pi bond. As we mentioned before, pi bonds are a lot more likely to break than sigma bonds because they're weaker and they are nucleophilic. That means they have loosely held electrons that can just pop up and catch an electrophile. Now, in this case, there is a choice between whether you want to put the electrophile on this carbon or this carbon. We are going to use hydrogen as your electrophile, and that would be governed by Markovnikov's rule. That's right. And Markovnikov said, when you have alkyl halides and you're adding HX across a pi bond, the hydrogen goes on the carbon that has more hydrogens, which means you are going to get a p orbital here that's empty. And your nucleophile can then come into your p orbital from above and below. Therefore, it's not really stereospecific. It's not saying, hey, I only want to go on this side, not on this side, guys, so make way. It goes on both sides because this is a flat carbocation. And then the steric bias and electronic bias is identical whether you come from above or below. Therefore, there is really no preference for either side. Therefore, it is not stereospecific. Let's do it. Here's the mechanism for this reaction. So here is your octene. HBr, as I mentioned before, can come in from above and below. And it's going to rip out that pi bond and add a hydrogen right here, H+. There's also bromide here, and you would have 2 options for this. It can attack on A or B termini, and so therefore you will have a positive charge either here with the empty p orbital, or you could have a positive charge on the terminal carbon. As we have discussed before in SN1, secondary carbocations are a lot more stable than primary. Here you have 2 hydrogens that cannot donate electrons to this empty p orbital. Therefore, this is going to be very high energy. So if you have a high energy intermediate, then your reaction is going to try to avoid that and go through a lower energy pathway. So this is going to be your lower energy pathway carbocation. So in this case, this is your intermediate and this is lower energy. And therefore, this is going to be more stable and it is going to be preferred. That means the energy to achieve this intermediate is lower. Activation energy is lower to get here than here. So why would it climb this huge mountain to get to the other side when it can just go through a tiny one? So that's what it does. Once it's there, now you have choices. You can have the bromide attack from either above or below. So let's say the bromide minus comes in and it can go in to this top lobe here, and you can get a bromide that is going to be above the plane. And here's your hydrogen, and it really doesn't matter, it's a methyl group. Let's call this A pathway. Or you can have the bromide attack from the bottom attack. This is top attack. And the bottom attack is going to give you a bromide that goes in here, and that is going to give you a bromine that is going to be on a dashed line. That means it's below the plane. And let's call that B. The bottom attack is going to have an arrow going to the bottom here. Let's look at what happens to this intermediate here, the high energy intermediate. That can also be attacked by a bromide, and the bromide in this case, it doesn't really matter whether it goes on the top or bottom because it's going to give you the identical product either way. So here is a bromide and you can attack that and you would get your product with a bromide that is just hanging on to the side here, and it really doesn't matter because it is achiral. In this case, you're creating a chiral center here and here. So this is going to be S, and this is going to be R. And therefore, you will get an R to S mixture 1-to-1, and that is called a raceme. Look at the numbers here. 49%, total 98% of this. Over here, going through the primary carbocation, it's only 2%, really very low. That means this is a lot higher energy than this. So 98% of the time you are forming this, and that gets attacked on top or bottom to give you the product, a 1-to-1. Because it's 1-to-1, there is no selectivity in the stereoisomers. Therefore, it is non-stereospecific. And 98% of the time, you're getting the 2-bromo-octane. And therefore, it is regioselective. You want to put your bromine on the second carbon here, not the first. So the region is also determined here by the Markovnikov's rule. So this is regiospecific, almost entirely here and not here. It is not stereospecific because it's a 1-to-1. You don't get more of one compared to the other. So it's non-stereospecific and regiospecific. The reason I'm emphasizing is because this is kind of new to you, and as we go along, you will see that you would get this right away. One of the things that's important to do is also find out what is the nucleophile and electrophile. In this case, you have a pi bond, and the pi bond electrons are the ones that are reaching out and catching the proton because they love positive or love a nucleus. Therefore, they are nucleophiles. And the hydrogen here needs electrons because it doesn't have any at this point. So therefore, it is an electrophile. After it attacks, now the tables are turned. This is positive, so this is your electrophile, and the bromide is your nucleophile. So this is your nucleophile. These are your electrophiles. And then you get your product. All right? Now let's look at it. There are options for this molecule. It's a secondary, but whenever a secondary can go to a tertiary, it would. Whenever a primary could go to a tertiary, it would. Because tertiary carbocation is the most stable out there. Can't beat it. So let's see what options are here for this molecule. Can this go to a tertiary? Turns out it can. How is that possible? I'm going to draw this out again so we can look at it. So the same molecule here, or same intermediate here. There are two options for this. As soon as it is formed, it can get wham bam attacked by the chloride. Okay, before it can think, it happens. All right. Now all these reactions are reversible. So let's say you get attacked by a chloride. The chloride is going to attack right here, and this is a secondary. It's sp2 flat, and so you know it's got options. It can go on top or it can go on the bottom. So there are two ways that it can attack. I'm just going to write top attack and bottom attack here. So if it attacks on the top, it is going to have right over here a wedge. If it attacks on the bottom, it's going to be on a dashed line. I'm just going to put these hydrogens, but basically this is a methyl group. And you can see we are forming these two, 20% and 20%. That's 40%. What happened to the rest? That's just a minor product. If this is a minor, well, what's the major product? Let's look at it. Here is a secondary carbocation. They're both the same secondary carbocations. And right next to it is a carbon that's got two R groups. Now, if you form a plus here, that would be tertiary. That would be a lot lower in energy for this molecule, and it would be really happy. So I'm going to put the hydrogen over here. And the hydrogen, when the orbitals are aligned with this, are going to just walk over, like take a stroll, go to your neighbors, just like that. And so you could see that the hydrogen electrons are going to be spread between this empty orbital and this sigma. So you have a sigma that is breaking and a sigma that is forming around that hydrogen. So that is going to be the transition state for that. And it is quite happy because it's got a tertiary center here that's going to form. So it feels like it's worth the energy investing in this hydride shift. Again, it's going with your electrons. So you're taking an H minus and moving it. And it's just between two carbons. 1, 2, hydride shift. So you're just shifting houses here. Once it goes over there, well, then you took those electrons, and therefore you are now going to have a positive charge here. But the molecule loves it compared to the positive charge on the secondary. So this is a tertiary carbocation, and that's the best. So this is very stable. Now when you're here, then you're going to get attacked by your chloride. And it can do up and down. In this case, it really doesn't matter because it's going to be achiral. And so your chloride lone pairs just into this empty orbital. And so you get a chlorine carbon bond. And your HCl then went across 3 carbons instead of just 2. That's called a rearrangement. So rearrangements are really common in Markovnikov processes. In this case, it's a 1,2 hydride shift. The reason why we specify 1,2 is because later on you're going to look at maybe 1,7 or other higher numbers. So this is just between 2 carbons, 1,2 hydride shift. All right, how much of this are you getting? You are getting 60%. So that is your major. So when you have rearrangements to tertiary, they tend to be the major product. These are your minor products, 40%. Let's look at what happened to our unstable carbocation here. Did it go anywhere? So let's look at this one where you have a chloride, and that chloride can attack again on this orbital. It doesn't really matter whether it's up or down because it's achiral, and that could in theory give rise to a molecule that's got an HCl across 2 bonds. Now, do you see any of this? 0. Okay, there's 0% of this. So even if you did form a primary, it would rearrange to a secondary, and the secondary then has options to rearrange to a tertiary and so on. And chances are you'd never ever form a product with the primary. So primary is very high energy and unstable. As I mentioned before, if you have a spread of products in a reaction, chances are it's governed by energetics. All right, so we looked at HX addition with rearrangement, and here it's without rearrangement. We're going to come back and see 2 more reactions with alkyl halides. Stay tuned, guys. I will see you soon.